Okay, so I just started recording. So last time we just started separable equations. So a separable equation means you can separate the variables x and y on the two sides so that you can integrate each side individually. Okay. So these are relatively straightforward. We talked about two examples last time. We're going to do a little more examples today. So this time we have a problem to solve the initial value problem. So that includes a differential equation and the initial condition. But the way to solve it is always the same. So the equation, the differential equation is dy over dx equals y squared minus 1 over x squared minus 1. And the initial condition is y of 2 equal to 2. Okay. So we're going to solve the differential equation first and then fix the arbitrary constant from the solution from the initial condition. All right. So to separate the equation, it's relatively simple. We got y squared minus 1 over x squared minus 1. So you can easily separate them to the left and right. By the way we're doing here. So you can divide by y squared minus 1 on both sides and multiply dx on both sides to get dy over y squared minus 1 equals dx over x squared minus 1. Good? Yeah, that should be straightforward. And then you just integrate on both sides. Okay. So to integrate a fraction of 1 over y squared minus 1 on the left and 1 over x squared minus 1 on the right, basically, you're going to rewrite the integrand in each side as a difference in this case. So that's called the partial fraction decomposition. If you remember, that was covered in 112. So basically, you can factor y squared minus 1 as y minus 1 times y plus 1. And similarly, you can decompose x squared minus 1 or factor x squared minus 1 as x minus 1 times x plus 1. And then you can rewrite the fraction of 1 over y squared minus 1 as a difference with the denominator y minus 1 and y plus 1. Okay. So if you do that, that ends up with 1/2 times 1 over minus 1 over y plus 1. And you can easily check that by, using the least common denominator of those two fractions, y minus 1 times y plus 1. And you're going to get 1 over y squared minus 1 if you do that. Okay, partial fraction decomposition means you have a rational function that you can decompose as a sum or difference of several terms based on the fractions of the based on the factorization of the denominator. Remember? Okay, but anyway, this is an easy, simple problem that you can easily double check. So similarly, you can rewrite the 1 over x squared minus 1 as 1/2 times 1 over x minus 1 over x plus 1. And then we can integrate easily each term on both sides. But you can cancel 1/2 on both sides first to make it a little simpler. So then 1 over y minus 1 and 1 over y plus 1, if we integrate, you're going to get the natural log of absolute value y minus 1 and y plus 1. Similarly, you got the natural log of absolute value of x minus 1 minus the natural log of absolute value of x plus 1 plus c. Okay, since we integrate, it brings out brings up an arbitrary constant. Now, one thing to be cautious is you have the absolute value in here. When you integrate 1 over x, for example, you get the natural log of absolute value of x. So don't forget that. And then you can do a little simplification for the result. If you combine the difference of the two natural logs, you just divide the two things. So on the left hand side, you're going to get the natural log of absolute value of y minus 1 over y plus 1. Okay. Similarly, on the right side, you get the natural log of absolute value of x minus 1 over x plus 1 and plus c in here. So now we can try to, determine the arbitrary constant c from the initial condition. Y of 2 equals 2. That means if you plug in x equal to 2, you should get y equal to 2. Or if we plug in 2 for x and y, 2 for y, and the solution should be valid. So plug in 2 for y on the left and 2 for x on the right, you're going to get the natural log of absolute value 2 minus 1 over 2 plus 1. And on the right, you get natural log of absolute value of 2 minus 1 over 2 plus 1 plus c. So you can see those two natural logs, one on the left and one on the right, they're exactly the same. Okay, 2 minus 1 is just 1. So you get natural log of 1/3 on the left and the natural log of 1/3 on the right. So they cancel completely. So that leaves c equal to 0. Okay. So the solution to the initial value problem is actually the two natural logs equal. Okay. Natural log of absolute y minus 1 over y plus 1 equals natural log of absolute value of x minus 1 over x plus 1. So that means the two things must be the same. When you take the natural log, you get the same result. That means the two numbers, you take the natural log, should be the same. So the absolute value of y minus 1 over y plus 1 has to be equal to the absolute value of x minus 1 over x plus 1. Okay. So now, if we want to, simplify further, then we have to get rid of the absolute value signs. Okay. So remember, when you take the absolute value of negative number, you get the positive number. So when you try to get rid of the natural log, the absolute sign, then you end up with both positive and negative. This is always the case. Okay. So y minus 1 over y plus 1 will be equal to either x minus 1 over x plus 1 or negative of x minus 1 over x plus 1. Because when you take the absolute value on both sides, they end up with the same number, right? So you can have a negative number and take that absolute value you get the same positive number. So that's why you always get a positive and negative. All right. Well, now we have to use the initial condition again to determine which solution is actually the correct solution to the initial value problem. If you plug in 2 for x and 2 for y, then you will see only the plus sign is valid. Okay, so 2 minus 1 over 2 plus 1 on the left, if you plug in 2 for y, and then if you plug in 2 for x on the right side, you get 2 minus 1 over 2 plus 1. And so you get 1/3 on the left and 1/3 to the right, with only the plus sign valid. Okay, right? The negative solution does not satisfy the initial condition. 1/3 is not equal to negative 1/3, right? So the solution will be y minus 1 over y plus 1 equals x minus 1 over x plus 1. Okay, and that's how you find out the right solution by using the initial condition. Okay. Then you can further simplify the solution by cross multiplier. Okay, this time we got two fractions on the two sides of an equation that you can cross multiply. Okay. So y minus 1 times x plus 1 equals x minus 1 times y plus 1. Now you just FOIL both sides. Okay. Just to do it term by term. Y minus 1 times x plus 1, you just multiply y with x plus 1, negative 1 with x plus 1. You end up with 4 terms on the left, and you do the same thing on the right. You get 4 terms on the right. So you can see if you do that, you're going to get y times x plus y minus x minus 1 on the left, and x times y plus x minus y minus 1 on the right. And you can do a lot of cancellations. Y times x and x times y, they're the same, so they cancel. Negative 1, they cancel. So what is left is just y minus x equal to x minus y, and then you can just combine like terms, move y and the x to the other sides, and you end up with 2y equal to 2x if you do that. Okay, so cancel the 2, so that becomes y equal to x. So the solution of this initial value problem is actually the function y equal to x. So the solution is pretty simple, right? Any questions for this example? I think the only thing that needs to be cautious is the absolute sign when you take the natural log. Okay. When you integrate 1 over x, you get the natural log of absolute x. That should be very cautious when you do problems. And the topic of partial fraction decomposition, when you try to rewrite the fraction as a sum or difference as fractions based on the factorization of the denominator, that's something that you should have learned in 112. All right. So this is the example for initial value problem of separable equations. Does anybody have any questions for this example? If not, then we'll just go to the next page. Okay. All right. Sometimes we may have some functions not integrable, but you can still write down the solution of the problem in the integral form. If you try to solve an initial value problem, you may not be able to actually integrate it analytically, but you can still write down the solution in the integral form. Okay, so suppose we have an initial value problem divided over dx equal to g of x. So that's a special case of initial value problem or differential equation. On the right hand side, we only get a function g as a function of x. It does not depend on y. So usually, the differential equation, the first order differential equation in this case will be dy over dx equals f of x, y. Both x and y appear on the right side. But in case when the right hand side of the differential equation is just function of x, then you can just integrate on both sides directly to find the solution with the initial condition y of x0 equal to y0. All right. So if you use the fundamental theorem of calculus, you're going to get a solution equal to the following: y equal to y0 plus the integral of g from x0 to x. That's the second part of the fundamental theorem of calculus. If you check Kyle 1, if you still remember Kyle 1. Okay. So this is the solution to the initial value problem of dy over dx equal to gx and y of x0 equal to y0. Okay. So sometimes we don't, we cannot actually integrate this function g, but still you can write down the solution in this integral form. So for example, if we want to solve the initial value problem of dy over dx equal to e to the negative x squared with the initial condition of y of 3 equal to 5, then you just use the fundamental theorem of calculus to integrate the differential equation directly and plug in x0 equal to 3, y0 equal to 5, the initial condition in the formula. So here the function g is e to the negative x squared. So the solution to the problem will be y equal to 5 plus the integral of e to the negative t squared from 3 to x. So you can see the solution to the problem involves the integral of e to the negative t squared that cannot be integrated analytically. But still, that's the solution to the initial value problem. So in order to get the actual function, if you want to plot this function, this is a solution curve, for example, then you have to use some numerical scheme. Okay, when you try to integrate e to the negative t squared from 3 to x, then you have to do the integration numerically. Okay, so what you do, you just pick up, values of x, and then for each specified value of x, you do the numerical integration of e to the negative t squared from 3 to x. For example, if I want to find what's the value of y of 4, so x equal to 4, so you just integrate e to the negative t squared from 3 to 4, find the numerical value, the actual number, plus 5. That will give you the value of y of 4, right? Then you just choose different numbers of x. So for each value of x, you get a different value for y. So then you get a bunch of numerical values. And a bunch of points that you can plot in the graph, and that gives you the curve of this solution, right? Okay, so that's this example. Any questions from this section? Okay, so I guess we just finished 2.2 separate equations. The strategy to solve separate equations are straightforward, even though sometimes they might not be so easy to integrate itself. You have to know how to integrate. Okay, but the principle is simple. Okay, so if there's no question from 2.2, then we just start the new section, 2.3. All right. So let me just open it, and then I think do I need to? Yes.
Are you going to start 2.3 right now?
Yeah. You got any questions? I don't see any questions. We still got the 12 minutes today. So do you want me to stop here or?
It might be better to just start a whole new section. So you want to have a section, like one half section for one half of that and do a whole new section for that.
Yeah, sometimes it's not the, I mean, there are some non-sections you cannot even finish it in 2 classes.
I understand that part, but it's just like for us as students, mentally, it'd be easier for us to just take one section at a time, and then we can process it, go and do the homework on it, and then we can come back and learn the next day. That's just how I feel like we should do it.
Okay, I can stop here today. If you want that way. So let me just stop here and see if we got any questions. All right. So